AVEVA's Unified Engineering is a multidiscipline, data-centric engineering and design platform. It unifies 1D, 2D, and 3D engineering design tools and process simulation into a single environment that enables engineering disciplines to collaborate without the need for separate design tool silos and staged handovers. Unified Engineering provides a fully collaborative, globally dispersed design environment that manages change and controls the workflow of data throughout the design lifecycle. This demonstration shows a process engineer modifying values in a simulation model. The model includes a green hydrogen plant design study with a wind power facility that had to shut down earlier this year during a major storm. Let's go through and evaluate this case. By leveraging AVEVA Process Simulation to create a simulation of these storm conditions, changing the wind speed to 20 meters per second allows us to see the subsequent power requirement for the pump, P1. Snapshots of simulation cases are stored, on demand, and released, all the way through to the detailed design engineers in Unified Engineering. Now, moving into the multidiscipline design environment, engineers can view bespoke lists of tags and their properties. For this feed study, the engineer receives notification of new simulation data and so proceeds to import the new high wind properties. Multiple cases are stored against the tag and are presented to the engineers in simple but powerful Excel-type lists. Unit conversion and case visibility are available at the click of a button. Opening a second list of functional tags allows the engineer to freely arrange the screen layout as desired. The flow of case data to the PFD tag is managed and controlled. Property values are able to flow from the simulation elements to the functional tags on the PFD, and finally, through to the physical engineering tag on the P&ID. The graphical diagram of the simulation model is also available. The engineer always has full control of the data flow and active cases. Selecting the case and pump to be updated, the data flows through to the functional tag, updating the property values. Related drawings for functional or engineering tags can be viewed at any time. Here, the engineer has opened the process flow diagram to view the functional pump and related tags. Off-sheet connectors allow for simple navigation across all related PFDs. Finally, the new high wind case data can be released through to the engineering tag, which is the physical pump. Now, the engineer will open the pump list. By doing so, and swapping the view from horizontal to vertical, and then switching to a side-by-side view, we can see the properties for both functional and engineering tags. Clearing up the desktop real estate, the engineer can now focus on the modifications required to add the second pump to the design. From the engineering tag, we can open the P&ID drawing which the tag appears on. First, the engineer can make use of the fully integrated design environment. It provides controlled access to all projects and their related cross-discipline 1D, 2D, and 3D data. Real-time access to the latest role and specific project information gives the engineer a complete understanding of the design and avoids any information blockages and silos. The 3D model view can be manipulated to display only the discipline data of interest and allows for complete focus and understanding of the tags involved in the design change. Focusing back on the P&ID, the project modifications can now begin by copying the existing pump. The tag ID is updated by changing the parameters specified by the project naming rules. The suffix is now set to A. The pump label on the P&ID is automatically updated, showing the new tag ID P1A. The new pump tag is also set by simply changing the suffix to B directly in the list cell. The new pump P1B is added to the P&ID simply by dragging it from the list view and dropping it onto the drawing canvas. A P&ID Explorer is also provided to allow simple navigation of tags associated with the current drawing. The engineer can quickly find the new nozzles belonging to P1B, which can now be dragged and dropped onto the pump. The default symbols can be changed at any time. This can be done by selecting from the associated symbols, which can be found in the project library. The Graphical Properties form provides a quick and familiar way to change the graphical definitions such as line type, column, color, and scale, etc. The associated pipework and components can now be added to the P&ID by dragging and dropping from the project symbol library. First, new branches are added to and from the new pump P1B, connecting to and from existing lines on the P&ID. Again, the P&ID Explorer provides a simple method of identifying the modified pipelines, and in this case, the engineer can highlight the line to confirm the integrity of the design. Returning focus to the symbol library, we can watch as the engineer now completes the new design by dropping valves, reducers, and instruments into the new lines. AVEVA's next generation P&ID provides an intuitive, intelligent, simple but powerful drawing tool, fully integrated with the 1D and 3D data models. This fully collaborative environment enables a single source of truth, avoiding unnecessary duplication, increasing productivity, and reducing errors. Let's now fast forward and rejoin the P&ID. Here, the last label is added to show the bores of the reducer. And finally, an attribute table is chosen from the symbol library to present the properties of the new pump directly on the drawing. The table is placed and rotated as required, and then associated with the pump via a connection point. The table now displays a selection of property values for the pump and associated motor. All types of graphical text update dynamically with property values, without the need for any manual interaction. Let's now move on to view some E&I work tasks. Opening up the list of electric motors, we can see at the bottom the motor associated with the new pump. This was automatically created as part of the original copy procedure. Even at this early stage, a datasheet can also be created using project-specific templates. Datasheets can also be used as an input window for further definition of the tag properties. Data can be entered directly into lists and datasheets, or via a number of other methods, such as import from third-party solutions, including Excel. Whichever method is chosen, the data is held directly against the tag. All lists are live views into the data model, and hence reflect the latest up-to-date information. Opening the instrumentation list, the instrumentation changes required for the new pressure gauges that were added to the P&ID can now be completed. After adding a description, the I/O type is defined by choosing from the library of project standards. Once the I/O is defined, the signal is automatically generated, as shown on the grid. Defining the instrument further, a wiring rule can be chosen from the project libraries. Wiring rules define the type and size of cable and core connections which are applicable to the instrument. The engineer defines the connectivity of the required wiring. From the list of available equipment, the terminal strip of junction box JB0001 is chosen. An estimate of required cable length can be added for estimation purposes. Once this connectivity is defined, it is possible to generate a preview of the complete wiring. we can now see the circuit is nearly complete. From the instrument to the junction box, through to the marshalling cabinet, and finally into the distributed control system cabinet. The final part of the wiring involves terminating the connectivity inside the DCS to the specific I/O module. This can be done via forms and lists, but it is also possible to complete this task more intuitively using graphical tools. The internals of the DCS are opened, showing the available termination strips and I/O modules. We can see the wiring for the new pressure gauge arriving at the terminal strip. Using this method, the engineer manually defines the wiring from the terminal strip to the terminals of choice on the I/O module. The respective terminals are selected and the wire created. We can now see the instrument signal is finally connected. Through to the I/O module in the DCS, this completes the required design update for the instrument. Now, the engineer needs to produce the updated termination diagrams for the DCS. Again, making use of project standard templates. The extensive use of templates and libraries ensures consistency, quality and compliance, and conformity to industry standards, whilst also avoiding costly mistakes and enhancing productivity. To complete the deliverables production, the updated project instrument list is also created within a few clicks. Like all drawings and deliverables in AVEVA Unified Engineering, datasheets are status and revision controlled. The last section of our demonstration focuses on the electrical discipline tasks required to supply power to the new motor. A schematic representation of the power distribution can be viewed, providing a clear overview of the project. The diagram displays the connectivity of the original pumps motor to the motor control center busbar. The key one-line diagram for this MCC can now be opened and modified to add the new motor. Using the related drawings functionality, there is no need to search through all project drawings to find the correct one. In a similar way to the P&ID, tags and symbols can simply be dragged and dropped as required. Opening the E&I specific Power Explorer window, the motor can be easily found and dragged onto the KOL. Once positioned, the connection to the bus bar is created, completing the KOL modifications. The Power Explorer now displays the relationship between the motor and the bus bar. To complete the cable sizing data is automatically calculated, containing the full details to match the power specifications of the bus bar and motor. After specifying some variable properties such as ambient temperature, the resulting cable can be designed. This can be done by selecting the spec from the project standards. The full definition of the cable is available on the cable schedule list. Next, the cable schedule is created again by selecting from the list. Finally, the load schedule for the MCC is updated. To complete our demonstration, we will move into the E3D design part of AVEVA's Unified Engineering. The power and benefits of the world-class leading AVEVA E3D design tool are well known throughout industry. Here we will see a very short workflow specific to the modifications required for our engineering change. After instantly locating the original pump tag, and by using the Explorer search bar, we zoom into the area of focus. It is a common headache during project execution that discipline-specific data, often held in silos, progresses at different speeds. Data is replicated many times, causing costly inconsistencies and errors. taking advantage of the fully integrated engineering environment. The 3D model can be aligned with the 1D and 2D data models at any time. Fully configurable, discipline-specific reports are produced, allowing engineers to make fully informed decisions, while also allowing disciplines to progress at their own pace. Here, we see the report highlighting the mismatch with the pump data in the tag register, the pump name change, and addition of the new pump, P1B, has been highlighted. The 3D model is updated with the new information, and 3D definition of the new pump is defined by reference to project standards and catalogues. Catalogues are shared across disciplines, ensuring project-wide data consistency and avoiding discrepancies between data models, which is a common problem between traditionally siloed spreadsheet of 2D and 3D data models. Once the tag has its shape defined, it can now be positioned in sight. Making reference to the existing P1 pump, we can simply type in an offset. The next task is to route the cable we designed for the new motor. Again, using the comparison report, we can use the system to automatically identify discrepancies between the master register and the 3D, and then create the missing cable from the resulting report. The new cable tag is now selected in the Explorer before defining the cable route. The full cable spec, including connectivity details, are available from the master register, so we now use the automatic routing feature of the system to produce the shortest, clash-free route that utilizes the closest available cable trays. By isolating the graphical view to just the cable and associated equipment, we can clearly see the completed route in real-world coordinates. Full cable tray details are also available, including routing node details. They are now assigned to the cable and can be passed back to the master register. Completing the design cycle back in the master register, a model comparison can be executed. This allows us to update the register with the actual cable route details and complete the new design tasks. Accepting the data from 3D, the route node details and real-world routing length are now displayed in the cable grid. As always, the 3D view can be used to give the electrical engineer a complete understanding of the pump and cable standing in the plant. Finally, the cable schedule is produced, which displays all the updated information for length and route nodes. This concludes our demonstration. Thank you for watching.